Hi, my name is Vincent Kang from Exoskeleton and Prosthetic Intelligent Controls Lab from Georgia Tech, and I'll be presenting our work on the continuous locomotion mode classification using a robotic hip exoskeleton. So, over the recent years, we've seen some exciting results in different research and industry groups, pushing the boundaries of exoskeleton technology. Some of these exoskeletons were able to demonstrate their capabilities in augmenting humans for improved mobility for healthy individuals and clinical populations. As different groups start to explore the optimal control strategies to better assist humans, we still face many challenges in translating these technologies to more realistic settings such as outdoors. One of the key user state variables that is directly correlated with the exoskeleton control is the locomotion modes such as ramps and stairs. These are some important environmental information as these are some of the common locomotor tasks that a person may experience daily. Therefore, accurately understanding the user's intent during locomotion is paramount to maintaining a maximal human exoskeleton performance. So why is it that understanding these locomotion mode information is so important? This is mainly because optimal exoskeleton assistant profiles are correlated with the user's biological demands such as joint biomechanics. Let's look at the case of the hip joint. As clearly shown with data, these 5 ambulation modes exhibit a different underlying joint moment, indicating that the torque assistant profile should be different as well. So how do we estimate the user's intent during locomotion? We use a sensor fusion modality by taking a kinematic sensor information from onboard mechanical sensors on our bilateral hip exoskeleton, such as the hip joint encoder and the 6-axis thigh IMU. By taking sensor fusion, we can extract out relevant information from each sensor to correctly identify the user's locomotion mode. A standard method in the literature is that these modes are classified in discrete times within the gait cycle from a deterministic joint configuration where the data is most reliable, such as heel strike or toe off. However, this could potentially result in providing a delayed and inaccurate assistance during the mode transition period. One thing to note is that during a gait cycle, these kinematic information varies even though the user stays within the specific mode, which makes the model hard to classify the user's locomotion mode accurately. To overcome this and achieve a continuous mode classification, we implemented multiple phase-dependent classifiers within the gait cycle. Additionally, we further improved the overall model performance by leveraging the bilateral nature of a hip exoskeleton system. With that, we made our central hypothesis stating that utilizing the user's gait phase information, more complex ML algorithms, and bilateral sensor information from the exoskeleton can further improve the overall model accuracy in locomotion mode classification. So how do we achieve a continuous locomotion mode classification? During locomotion, different features are extracted from mechanical sensors such as encoders and IMU on the exoskeleton. The user's gait phase information is utilized to choose a relevant phase-based mode classifier during the gait cycle. For our mode classifier, we implemented a Bayesian strategy with varying complexities such as naive Bayes, linear discriminant analysis, and quadratic discriminant analysis, which are some of the common machine learning algorithms that have shown decent results in mode classification. To further improve our steady-state classification accuracy, we implemented a dynamic Bayesian network, which is a filtering technique often used in a time history-based classification, leveraging a Markov assumption with a probabilistic representation. To test our hypothesis, we recruited 5 able-bodied subjects and asked them to walk on an in-lap height-adjustable terrain park consisting of overground ramps and stairs with our robotic hip exoskeleton. The terrain park height was adjusted and set to 4 different stair heights and ramp inclines which were in the ranges of a standard ADA accessibility guidelines for buildings and facilities. Each subject walked in 5 different locomotion mode conditions: level ground, ramp ascent and descent, stair ascent and descent. For each mode, the subject performed 8 trials where the 4 trials would consist of left leg transition and the other 4 were right leg transitions. Throughout the experiment, the order of the ramp and stair heights were randomized, and the exoskeleton was controlled in a zero impedance mode. During the experiment, we recorded onboard bilateral mechanical sensor data such as the hip joint encoder and the 6-axis thigh IMU data. First, we explored the effect of adding phase-based model within the gait cycle, and indeed, our model performance improved with more models which was shown consistently across all 3 classifier types. For all models, similar trends were shown where the overall performance converged after 5-phase models. Across all algorithms, using 5-phase models reduced the relative classification error by 35% compared to the 1-phase model. Interestingly, this optimal phase number was relevant to the gait phase segmentation from a gait biomechanics perspective, which correlated closely with the stance and swing face dynamics. Next, we explore the effect of model complexity in the overall classifier's performance. For both unilateral and bilateral feature conditions, each step of model complexity yielded significantly better transitional performance. However, a similar trend was not exhibited in the steady-state performance. Mainly, QDA using bilateral features increased the steady-state error compared to QDA using unilateral features. This may be due to the cursive dimensionality that the number of features provided to the QDA model was not backed by the size of the dataset, which can cause the model to overfit. This study indicates that the LEA algorithms again represent the right level of complexity for Bayesian mode classification, similar to many results in the literature for locomotion mode classification. Lastly, we looked into the effect of using a bilateral sensor information. Utilizing the bilateral feature information was able to further improve the classifier performance. The results show that fusing bilateral features can reduce the overall classification error by 43%. Our leading and trailing limb analysis indicates that utilizing the contralateral leg's feature information can help the ML model to improve the performance during transitional gait cycle. This is mainly due to the contralateral leg providing meaningful information as it is already transitioned into the next mode during a trailing limb situation. So some of the discussion points from our study is that 1. Optimal level of complexity in the ML algorithm can maximize the classification. Second, multiple phase-based classifier during the gait cycle can reduce the classification error. Lastly, utilizing bilateral sensor information from the exoskeleton can further improve the classifier's performance. One of the limitations of our study was that this was an offline analysis. Literature studies indicate that real-time performance can have an effect on mode classification performance, which is not accounted for in an offline analysis. Therefore, ML model performance validation in real-time implementation is needed for future studies. Another future direction from our study is to test our model performance with different exoskeleton assistants. Our previous studies indicate that depending on the exoskeleton assistant level, users' gait dynamics can change. This can potentially create variance in sensor signals which may affect the overall classifier's accuracy. Lastly, our optimal model leveraged bilateral sensor information from the exoskeleton. While this was possible for healthy individuals with a symmetric gait, the effect of asymmetric gait in clinical populations such as hemiplegic gait due to stroke is unknown. Future studies can implement a more robust ML strategy to accommodate such shift in the data distribution.